Good morning or good evening, everyone, depending on where you're joining this live stream from. First of all, Happy New Year. This is the first session from AI Engineering this year, and I hope we see more such learning sessions throughout the year. And today we have with us Hassan Rafiq. Basically, Hassan is both cloud and ML engineer. So from his profile, you can see like he comes from both the machine learning development side, and the second and major aspect is how you can scale this machine learning into production systems. He works as a senior consultant in a top tech consulting firm. And what we are going to basically see today is an end-to-end machine learning development using TensorFlow and how to build enterprise scale big data machine learning system. Basically taking your machine learning model, creating a pipeline, and how you can put it into production. We will see a lot of information about TensorFlow, about real world systems, and also some of the new features of TensorFlow. Without further ado, I will hand it over to Hassan. Hassan, it's up to you. You can go ahead now.
Thanks. Thanks, Watson. And Happy New Year to all. First of all, that's like a thing which I wanted everyone to be like be wished. And we're going to talk a lot about TensorFlow as Watson already introduced. And just a thought from my side. So anything that I speak today is perspective to my thoughts itself. It's not reflecting or responsive or representing any firm's way of working or of that sort. It's all my personal experience that I'm showing. Without further waiting, let me start. So I think we have a lot of, you must have heard about TensorFlow as a term somewhere, even if you're not very much attached to machine learning or data science. I'm pretty sure this is a term which you may have seen either on LinkedIn or Google. And if you have read about these blogs or heard about things like self-driving cars, text translation, and all those things. And let me start with the introduction. So what actually TensorFlow is? TensorFlow is a free and open source library for machine learning by Google. It was initially built by Google starting in 2011, and then it was released in public for open source use by general public in like 2015. And it can be used across a range of tasks. I mean, you can build graphs actually. So you can create you can represent your task. For example, you want to add two numbers, you can create a graph of like two inputs going into an addition operation, and you can say that it's an input as a function. And primarily this library is used to create deep neural networks. So it's like you can create a series of operations, you can create a series of layers. A deep neural network is like it's like a neural networks artificial representation. So our brain is a network of neurons actually, and we won't be going in that depth on those lines. But a deep neural network is a neural network which has more than one hidden layer actually. Okay, so going further, what I can say is that TensorFlow actually looks like this. I mean, this is the high-level architecture of what TensorFlow is. At the lowermost, you can see that it's the hardware layer. TensorFlow can run either on your CPUs, which is like a normal processor, a GPU. A GPU is a graphics processing unit, like a graphics card. You have different organizations and hardware firms which provide graphics card on which we usually game, and that is when we hear about these terms. It can also run on Android, iOS, and XLA is like a runtime environment for that. And on top of it is our TDEE. Basically, that's called the TensorFlow Distributed Execution Engine. It allows TensorFlow programs to run on distributed hardwares. So it's like if you have heard about these frameworks like Spark, for example, or Hadoop, which have the capability of running on multiple cores, TensorFlow provides the same architecture. It provides the same capability. You can run on more than one CPU, more than one GPU, and it can also be a hybrid of CPUs, GPUs, and in fact, even TPUs. On top of it, you have different things like you can code it either on Python or C++, Java, Go, and in fact, you can also do it on JavaScript now. This diagram is from 2019, actually. It's not updated, but there's only one edition, is like JavaScript. And that's called TensorFlow.js version, on which you can directly run machine learning models. You can train them in your browser itself. And on the left-hand side, if you see, if you use it with Python or C++ or Java, for example, TensorFlow also provides you high-level APIs, also called as estimators or Keras model. Estimator is an API in TensorFlow wherein you can build model directly by specifying the layers, number of layers, the number of neurons in the layer, and that's it. The activation and learning rate, and that's it. You don't have to specifically go and code the nitty-gritties of a neural network. That's all controlled inside the API itself. And then the second version, which is the latest edition, is the Keras model. Keras was earlier a library built by one of the Google engineers, wherein he took all the functions from TensorFlow and converted them into high-level APIs like different types of layers, neural network architectures, and created small functions that you can connect together to create a high-level architecture of a neural network. All right, so going forward, we would actually be covering the TensorFlow version 2. TensorFlow version 1.0 was released in 2014 late year. TensorFlow 2 was released somewhere in like mid 20s, sorry, the early 20s, 2020. And right now we are working on 2.4. That's the latest stable release for this version, TensorFlow 2.4. All right, and the dataset that I would be talking about specifically in this whole session is the the New York Operations Taxi openly available taxi dataset. So what this dataset is, so in New York, any taxi that you take, it's billing information that where the taxi was taken, where the taxi dropped a person, how many riders were there, what was the date and time, and everything, what type of cab was it, and how much was the fare and tip. Everything is recorded. It's kept in an open data set for people to use for different sorts. You can run surveys, you can run data science, you can do analysis and build your models on it. Now, what we're going to do in this problem is we have a data set with these 18 features, and I bolded this one fair. So we are going to take all this information and we try to predict that if a person is going to take a cab from this place to this place on this date, this date of the time, this date of the year, this time of the day, then what should be the estimated fare? Okay. Now, this data actually, and if you take the complete data, that is more than 500 million records. It's more than 150 GB of data, and I'm sure there would be some people on the stream right now who would know pretty much a lot about machine learning, and there would be some people who may know a little bit. But one thing which everyone knows really is that there's something called as a memory, or that's the RAM, and on a machine you can only load as much data as is supported by your RAM. So 150 GB of data to be loaded in a machine RAM at once is impossible. That's where TensorFlow pipelines and TensorFlow scalable pipelines and this comes into play. So here is what we're going to actually talk about, is how we can build pipelines that can scale to so much of data, and you can build machine learning models, deep learning models on this much of information. All right. Okay, so what we're going to do here is now I'm loading some important libraries that we're going to use. So we are going to use pandas, and I'll tell you why. We're going to use Seaborn for visualization. We're going to use Matplot for visualization. Folium is a library that allows me to visualize GIS information, that is global information, that is geographic information. Actually, we have latitude and longitude in our data set, and we want to project them and see them on the screen. Then our usual TensorFlow is what we're going to load. Currently, I'm running this on Colab, and I'm going to connect to a CPU version or a GPU version. That is what you can do. And you don't need anything outside this notebook, actually. You don't need any other file. Everything is done in this notebook, and we would be sharing the link right at the end of this session as well. So here you can see that what I'm doing is I'm going to run a distributed training. Distributed means this training can either happen on a CPU, it can also happen on GPU or on TPU. Google Colab, this is the Google Colab environment. Google Colab provides me free GPUs and TPUs for training. And I have said right now that I'm going to train this on a GPU version. And this is a TensorFlow code through which you can actually strategize your code to run either on a TPU or a GPU. If I was running this on a TPU, this is my fixed 4 lines of code. You don't need to do any change over here. You can simply use this code and your code will start running on TPU itself. But what I'm doing right now is I'm using a multi-worker mirrored strategy on GPU version, which means that I'm telling my TensorFlow that it has to take my whole code and copy all the hardwares, create a mirror, copy all the variables, sorry, and put it all on all the available GPUs that are there. Okay, so what I'm doing is I'm going to run this on my system, and so it says that there is one CPU available, and it has converted this to a single worker strategy. Um, Next, what I'm doing is, so this is a diagram which is a very good representation of what the training and deployment in TensorFlow looks like actually. So on the left hand side, you can clearly see that we talked about TensorFlow estimators and Keras that were available. Underneath, I talked about the distribution strategy. So there are three hardwares that you can use: CPUs, GPUs, and TPUs. And there is a dashboard available, also called as tensor board. So a tensor board is like a graph. It shows you visually that what is happening during a training process. So you can see the losses, the iterations happening. You can also visualize your TensorFlow graph that you create. And once you train the model, once you save it, it saves as a saved model file with an extension of PB or PBTXT. It is a huge folder that is created with all these formal factors in it. And then also all the TensorFlow models. So there is also something called a TensorFlow Hub, which we are not covering in this session, but is of a different aspect. It provides you pre-trained model that you can use for transfer learning in your problems. Then once your model is trained, you can actually deploy it in three options. One is either you can deploy it as an API or as a gRPC API on TensorFlow serving. You can deploy it on an Android or an iOS app as a TensorFlow Lite model. And if you want to run it on a TensorFlow.js on your browser itself, then you can do that as well using the TensorFlow.js library. Okay. Next is I am going to copy the dataset from GitHub. So this dataset is all open source. And once again, let me repeat: all the dataset and options and all the components that we're using in this session are all open source, openly available. So there's nothing proprietary or something specific to that you can't use. So within Google Colab, you can run non-Python code as well. You just need to specify this exclamation mark, and you can run Unix commands, the operating system level commands. So I'm saying wget. Wget means download the dataset from the file, from the location, and I can see the dataset available over here as a data.csv file. Okay, let's move next. At a high level, since we're talking a lot about machine learning, beyond machine learning, actually, it's more around the DevOps of machine learning. The DevOps of machine learning is actually called as ML Ops or ML workflow. And this is what we're actually covering up on a high level right now. But there are more, I would say, advanced concepts in ML Ops specifically, which we're not covering, but this will still give you a good idea of what we're doing. So any ML machine learning workflow typically contains of 5 steps. The first one is data processing, wherein we download the data, we run some descriptive statistics, we also cleanse the data. For example, if you download data, there are nulls, there's some garbage information, there are some empty rows, empty columns that are not available. You may want to cleanse your data, and this is very specific to your problem statement. So there is no Bible around it, but it depends upon the problem statement that we're trying to solve. Okay. The next step is data exploration. So we are going to apply statistical approaches to understand the data. So we're going to apply exploratory data analysis and visual data analysis to understand how my data is showing different patterns, what are the different attributes in my data that are available, how are they correlating with each other. And this will also help me create new features or new calculated attributes that will show. New features actually help us train the models much quicker. And all this information that we'll be taking from the data, we are going to put this in a TF.Data pipeline. This is the pipeline. This is the main component of this whole session that we want to cover up. So TF.Data ingestion pipeline is a highly scalable data ingestion mechanism into TensorFlow that can ingest infinite scale data. And with infinite scale data, I actually mean infinite scale data. So even if you have petabytes or zettabytes of data on which you want to train model, which are like larger than live data sets, then you can still use this pipeline component to build model and ingest data into your model and run the training at scale. Finally, we are going to cover up how we are going to build our simple wide and deep neural network model. This is an architecture that we're going to use. It's a state-of-the-art model that we use for categoric for the data for data which has different sorts of elements like categorical data signals as well, plus numerical signals as well. And I'll talk a lot more about this. And then in the end, how we're going to deploy this model. This is a highly representative information of the pictorial view of what the whole process looks like. And I won't spend much time here. Quickly loading simple things. What I'm going to do is now I've taken a sample of data. I told in the beginning that the data itself is like huge, 500 million records. But what we have done is we've taken a small set of data, which has only 15,000 records, downloaded it from Git. And this is a machine learning step as well. You may have a lot of data, like 1 million or billion records, but you may want to take a small subset for your exploratory analysis, feature engineering, statistical search, and all those things. So you take a small data set like 1 million records, and it's not for training, it's only for analysis. This process is called as sampling. Okay, where you study your data set, create new features, understand things, and then you apply this on the whole data set. So the idea is you take a sample first. That is what we've done over here. We loaded the data. We're going to apply pre-processing on the small data to understand different aspects of it, EDA and BDA on this. Then we're going to apply the same things. We're going to take all this information, put this in our TF.Data pipeline, apply it on the main data, that's the bigger data, the 1 million, 1 GB, sorry, the 1 terabyte or 2 terabyte of data, whatever we have, and train the model on this. Simple stuff over here. You can see we have 15,002 entries, 18 columns, like float, integer. Some of them are null, some of them, like this one, has only one record. This one has only 9,800 records. All those steps are here, and this is not what we're going to cover up in this session. So I'll just quickly skim through to save time for the better things that we're going to talk. Quickly, we're going to check what are the number of records that we have in each column. So n unique method on a data frame gives you this thing for each and every column. So it tells me that, and this is regardless of whether a column is textual type or float or integer. So it gives me this good statistics. It tells me that some of the things that I would like to talk to you about is the trip start month. So it tells me that in every record, I have data for 12 month, 24-hour, and 7 days. So I also have the timestamp. So the data looks like this over here. So it's like pickup community fair. This is in dollars. Trip started on 5th month, 19 hours, 6 days. Like I believe if you start from Sunday, then it's probably Friday. Pickup latitude, longitude. So some of these records, they don't have nans. We may want to drop them once we want to build a model, and this is something which we'll talk forward basically. And they pick up latitude and longitude. What was the trip distance? What is the payment type, company, and trip duration and all. Now, now our problem is more around we want to predict the fare of a taxi trip before it starts. So it's very logical that you may not have a lot of things available before you start a trip. For example, I may know the pickup location and the drop off location, but I may not know what is the distance going to be. Let's say there's going to be a traffic jam, or let's say I want to take a different route. So these things can change. If you've used taxi apps, then you know usually at the end of the trip is when you know the total distance and the total duration. So we're going to do the same thing. We're going to drop the useless columns. I mean, useless is a different term, but those columns which we won't have during the prediction time. Okay, so we're going to drop some other columns as well. So I want to drop trip start timestamp because I don't know when I'm going to start my trip exactly. I mean, it may be like in next 2 hours or 3 hours. So I just wanted to take a assumption. Trip miles I won't know before I start a trip. Pickup census. This is more like a column which had only one record, so I want to drop it. Drop off, same thing as pickup census. Trip seconds. Definitely, I won't know how long my trip is going to be. Payment type. I don't want to put this as a feature in the model while I'm training it, because I may want to change it at the last moment. At the end of the trip, I want to pay it with a card or with my mobile app or with the cash and all. Tips. This information is actually very much correlated to the 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 fare. That's why I don't want to leak this information to my model when I'm training it. So I'm dropping it off. Similarly, company, drop off community area, pick up community area. I don't want to use this information, and I've said drop this all these columns. So out of all the 18 columns, I've finally said use these 8 columns. All right. Other than that, what I'm saying is, so some of these things are like I want to convert them into categorical. So first, I'm dropping all the rows which had any null value. So you saw that there were some null latitude and longitudes. I simply want to drop them. Then I'm converting some columns from, so these are all integers, basically month, hour, and day, but I want to make them as categorical. I want my model to take them as categorical. And why categorical is because these are not measurements. You cannot measure time, actually. I mean, you cannot measure month, hour, and day. You cannot add and all those things. I want to take them more as a categorical attribute, and let the model learn on that. So I'll execute this part. This is plain pandas functionality. I come to this thing. These three get selected. Now, before I do any exploration, so this is a very good point, and most of the people they do mistakes when they are doing machine learning. People usually run statistics, exploratory statistics, on top of the full data that we have available. I mean, it's like people don't so but our point is, whenever you do exploration, always do exploration only on the training data. Don't do it on your validation data. So it's like you need to split your data set into two, at least two or three partitions, and you only need to do only need to do your statistical learning and searches only on the training data, so that you don't so that you're able to actually validate all your learnings and your model on the unseen data, which is the holdout set or the validation set, and then finally on the test set. Um, and then, so after doing this split, it's a very simple step that we're using. Finally, we're saying that I want to split this in 85-15 ratio, at 12,300 records over here and 2,200 over there in my training set, in my validation set. All right, so this is the interesting part, the slightly more interesting part we are doing. So I want to see the skewness of fare. I plot this information and I can see that my data set is right skewed right now. Most of the data is the fare information is like lying somewhere between 0 to $10, and I can actually see it over here as well. So once you run the descriptive analytics on the data set, fare shows me that the mean is 7.85, sorry, 11.76, but 50 percentile, that is the median information, is somewhere 7.85. So this departs, or this actually tells me that my fare was right skewed, which is also visible over here. Now skewness typically is an important factor, and you may want to scale this so that your data becomes properly visible. I mean, it's like you should have the top curve somewhere in the middle. You may want to remove the outliers from the data set, but we're not covering up all that information over here. And I'll actually show you how you can build models that can also handle the outliers. So this is something which I'm not going to fix over here. The next information that I want to present is, I wanted to see that, as per the pickup information, what is the fare? So I've created a very pretty looking graph over here. So if you can see that all the trips which started from here, um, actually, and this area is somewhere in Lakeview. These trips are the most expensive. So the map is showing latitude, longitude information, and heat map color is coming um, as per the charge of the fare, or the fare that is on the trip. Okay, so this is something important, and I've only drawn this to see what are the patterns, and is location actually making a difference to the trip size? So it actually makes sense. Now, taking this information, what I'm going to do next is, this is another feature engineering information or technique. So you have seen right now that we have latitude and longitudinal information. Okay, so far, a lot of you would have seen how to handle numerical information like height, weight, sensor values, age, salary, and all. But but the way that we handle global information or geographic information is slightly different. We can't handle it as a categorical or numerical information. We have to take somewhere in between. So what we usually do is we like to bin this information. So in short, what I would say is that if my model could take some of this information, that this area is like, if my trip starts somewhere over here, then this strip actually looks, then this would actually be a high fare strip. And if it starts somewhere over here, then it could be a lower, it, my trip fare would actually be a little bit lower. How can I code this information in my model? It's like, if I can say that if the area is somewhere over here, then it's a low trip. If the area is somewhere over here, then it's a high value trip, and similar of that information. So I've talked a lot about it, but how can I actually make it is if I can somewhere divide my whole graph as a grid. Okay, if you would have seen the atlas, we have latitudes and longitudes, and each intersection of a latitude and longitude of two latitudes and longitudes creates a square or a rectangle, which then creates a grid. So essentially, we're going to take the same information and I'm going to distribute. I'm going to create regions in my whole map and create bins out of it. So in pandas, you have something called as binning. Sorry, and this is a feature in machine learning where we bin our numerical information. So we create bins out of it. So I'm binning my latitude information into 20 bins, and same thing for my longitude. And these bins are not equally spaced bins. I'll run this command and I'll show you my output. Let it run. Okay. So this is my latitude information. This is the distribution of latitudes and longitudes as it was earlier. And after I binned it, so binning, these red lines are how I created the boundaries of binnings. So you can see anything which had a lot of information, lot of values available in this area, they got small. I mean, those bins had like small gaps, and things which had like less density, they had broader gaps. So this is my bin boundary. So I'm going to say that anything which falls between latitude 41 point, let's say 66 to 41.86 is going to fall in this bin. Anything which is in where is going to fall in this bin, so on and so forth. Okay, rather than representing my information as numerical form of latitude and longitude, I'm going to call that as that my latitude is bin 3, for example, and longitude is bin 5. Okay, now so let's say bin 3 of latitude falls somewhere on this line, and longitude falls somewhere in this line. So that would actually mean intersection is that this is the bin, and this is how we actually code our information for latitude and longitude. It's a very clever trick, and it absolutely works a lot better when we build our models on this scale. So this is some feature engineering that we are going to apply on this column, and this is one information that we're going to take forward. Next is I'm running some other statistics, so I want to see whether my fare makes any sense with the trip start hour. It's a Boolean plot from Seaborn. So since everything is falling over here, I don't see much correlation alone with trip start hour. And similarly for trip start day, it does not make a lot of difference. But what I want to show you is that if we combine both these information together, actually, so, and this is also again how we are busting a myth. So two attributes, if we look at them together, I mean, if we looked at them separately, trip start day with fare and then trip start hour with fare, it did not make a lot of sense actually. But when I combine them together, so I say I want to check what is the average fare for a day within an hour. Okay, for a day in an hour, and here I can see a clear correlation. So if I start my trip early morning, around like 5, 6, 7, and then my trips are usually very expensive. So the gray scale tells me, the black thing tells me that my trip is very expensive. And same thing over here. This is my number of trips graph. So it says trip start day, trip start hour, and I want to count the number of trips that happen. And this is again another information that I'm going to put in my model. So it says that at the night hours, usually around like 8 p.m. to around 11 p.m. and then even till 12 p.m., I usually have high number of trips. And this is the best way to look at what's happening together when you want to see more than one attribute, how it is making sense. So this is something that I wanted to talk to you about, and all this information we're going to take together in our model. Actually, how we're going to combine these two models, because models cannot come up with these correlations by themselves. You have to do feature engineering, give the model a hint to get trained, and increase your training accuracy and reduce your training time. So feature engineering helps you on all those steps. Now we've talked a lot about feature engineering. And this is what we're going to do over here. So one thing that I wanted to add here is like in feature engineering, we combine more than one. So we combine two or more than two attributes to create new attributes. What we're going to do over here is like when the trip. So we definitely know that the distance of a trip makes sense. I mean, it affects the fare. We know it's an intuition, but we're going to prove it specifically even by looking at the data, because intuition is not what works in data science and machine learning. We have to give proofs to everything. So what I'm going to do is, if we could find a way so that we could calculate the trip before calculate the distance of the trip before it starts. So I've created a small function called as Euclidean, which is a very simple mathematical formula. If you know, I would say the geometry actually, when you have a point on the graph marked as x and y, x1 and y1, and then you have a second point x2, y2. Euclidean distance is a distance straight single point distance, like point to point distance of a straight line. Though this is not the real distance of a trip, because you can have a car moving at a different roads and routes, but this will still give you a good idea of how too far are points actually on the graph. There's also a radiant distance, but I've not applied that formula over here. I just wanted to keep it simple for everyone. So I created this new extra feature called as distance using the Euclidean formula a comma b. This is again a SciPy library feature, and then I'm multiplying it by 100 to scale it so that it becomes quite scalable. I mean, it looks in values of 0 to 10 and 50. So it says that, for example, this strip which has fare 12.25 at distance 4 kilometers and so on and so forth. Now I want to also see whether my trip fare is actually affected by the distance, and here you can see that I plotted the distance on the x plot on the x-axis and fare on the y. You can clearly see that it's a clear correlation between your distance and fare, because everything is lying on this axis. The width is quite high, which tells me that there is a lot of unexplained variance, and that's possible because even the trip's date, the time of the day and hour, the type of cab and all affects the location and all affects. So this is what we're trying to predict in a model. All right, and I've also created a univariate distribution plot. So I can see that most of my trips are again lying on the left-hand side. So this is again right skewed, but some trips, they have long distances as well, somewhere around like 28 miles and 30 miles. They're huge trips. Um, Again, so what I'm going to do now is, okay, so these are the same graphs that I was plotted earlier. And again, so what we're going to do next is we're coming at the main part of the session now. So we've seen a lot around how to do exploratory analysis of a data set, how did we do feature engineering, how did we study the data and all. Now I want to apply the same information on my bigger data set. It's like I have 500 million records, or even more than that. Let's not give it a number. Let's call it infinite scale data. I don't have any number around it. I like to call it infinite sized data. And how can I actually apply this thing? Um, so what we're going to do is, we took a data so far which had only a sample, and we explored it in pandas. We explored it in pandas. We cleansed the same sample. We've not applied it on the full data. I want to repeat it. We have not applied any cleansing, any pre-processing on the full data. We have not done it. We've just done it on our sample size. Okay. Now what we're going to do is we're going to take that same information, same knowledge of pre-processing and cleansing, and we want to apply it on our bigger data set during the training itself. So what we're going to do is we're going to use something called as TF.Data API. It's an API available. It's an API which is provided inside TensorFlow, through which you can build pipelines. This pipeline reads data in batches from files. So if you have multiple sources like files or database or even web sources, you can read data using this API, using this pipeline API from those sources in batches. You can apply these same processing features, processing functions on this pipeline in batches, and the output is then sent to the model for training. So this is a very good pictorial representation of this thing. So it's similar to an ETL process, which we also study in data engineering. You extract your data. So this is the TF dataset section. TF dataset extracts the data from source, transforms it. Transformations means all the feature engineering and all that you want to run, scaling and all, and then loads it into the model. So this reads like 500 records at a batch, transforms them, sends it to the model, picks up another 512, transforms it, and this process keeps on happening. So once my dataset API has passed um, the full dataset, 500 million records into the model, that's called one epoch. Okay, I may want to run my whole process for 2 or 3 epochs, my whole training process for 2 or 3 epochs, and that's why machine learning training processes can range for days if you have a lot of data. So, for example, when these firms like Google and all, they train big models, big computer vision models and all, when they train them, their training processes, if you've read in white papers that they've released, lasts from like days to certain weeks and so on and so forth. There are some best practices how you can tune a TF.Data API, and this is for experts that we may have on call. There is something called as prefetch, interleave, and map. Prefetch is when you want to when you tell your model, your pipeline, that it can pick up more than one batch of data at once. So let's say my batch is 10 records. I want to tell my pipeline that don't just pick up 10 records, pick up 20, 30 records at once, so that my CPU does not keep on waiting for the training. Because the training part, that's this part, runs on CPUs or GPUs, but this one, it runs on your CPU itself. So since this part is quite fast to execute, it may wait for the IO, the data available, and then IO is a slightly slower process. So data set extraction may be slow, and my CPU may be waiting idle. So to fasten this up, you have things like prefetch, interleave, and map. So with this thing, with interleave, interleave is a concept which reads multiple files. So you may know that there are a lot of files which are like bigger in size, but in machine learning, what we preferably do is we chunk the data, also called as sharding. We split our huge data set into small files. Like if I have 500 GB of data, I may want to split them into um, like 100,000 files of like size 500 MB or 20 MB or 250 MB, so that I mean, I have better visibility and better maintainability on my data and all. So interleaving means I am telling my pipeline to open multiple files at once. It does not have to pick up any single file. It can open multiple connections to multiple files. It again fast speeds up the process. All right, moving to next thing in feature engineering. So this is a small function that I've created. Uh, since I created a feature on the top for a new feature called as distance, I'm going to use the same formula inside my feature engineering pipeline as well. Sorry, the data pipeline as well. So I'm created a small function called as feature engineers, where I'm going to add new features. I've added only one feature here, but we may want to add more than one features and all. That is something that we can do. And I'm going to execute this thing. Now the whole magic of the TF.Data pipeline is happening in this step actually. So I've created a small function called as make input function. My input function is my gateway to the pipeline. Inside my make input function, I actually tell how to create I'm going to create my own pipeline step by step, and I'll walk you through it. So my first step is I'm telling my pipeline that open the files that have been provided as a parameter called as file name. So in this file name parameter, I can either provide a direct file name, for example, train.csv. I can also provide patterns of names. I can say train star.csv, train asterisk.csv. So any file that follows this name pattern train will be picked up in this pipeline. So this comes up handy when you may have multiple files like train 001, 002, 003.csv, and that is when it comes into over here. Next step is I'm telling that if I'm running in training mode, if my pipeline is being called in training mode, then I'm telling that uh, this pipeline should be feasible to run any number of epochs. Okay, I can set my epochs in my training in my model itself, but in my pipeline, it should not be dependent on the number of epochs and all. That is what I'm telling. And if I'm running evaluation mode, that is when I'm trying to predict or evaluate using this pipeline, then it should only run one epoch at max. Okay, it may run a smaller, it may pick up only one batch from an epoch, but at max it should only be ready for one epoch. Next thing is I'm telling that I want to read CSV files. So this is a function in TensorFlow. It is available from V1 actually for now. It will be transferred in TF2 with another function. But I'm telling that from V1, all the files that were picked up in this step, pick them up, take the batch size. I've right now defaulted this to 5 and 2, but I can change it in my function. read all the CSV columns. So CSV columns are coming from my train files columns that were there in pandas. Column defaults. This is something which is important. So all the columns that you're passing over here, you should also pass a default value. So in case if TensorFlow finds that array of the column was like null, so what should be the default value that it should use in this case? Because TensorFlow does not understand nulls. It has to provide a default value. Then what is the label feature? So I'm telling that my label is fair. I want to predict fair. Number of epochs that I want to run, parallel reads. Then I talked about the prefetch thing. I talked about some TF.Data best practices. So I'm applying them over here. And then the good part. So I'm also applying feature engineering inside my pipeline over here right now. Okay, so what I'm telling my pipeline that pick up these 8-9 columns and also create the new feature engineering features. So it'll pass my data into this function. It'll create a new features called as distance and give it back to me over here in this step. Then I'm going to shuffle my data, and I'm telling telling my pipeline to repeat this for the number of epochs, this whole process. That's it, it's done. It's as simple as that. You can take this function and you can just directly put it for any problem statement that you use. I use this even for image dataset. And you just need to be a little bit experienced with TensorFlow, but you can write these functions and it's very easy to run them. Quickly, how you can test it. So I'm taking the same make input function. I provided the file name over here. I provided the mode, and I'm saying that pick up 10 records. I'm going to run it. It has clearly given me 10 records from my file. Okay, and over here I can see each and every record, so that is available. It is also giving me the distance thing over here, which is available. So it has the distance was not available by default in the training file, but after feature engineering and in the dataset, it's available, and you can see values for them. And you'll only find 10 records: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So now next is this data in this format will be taken into a model and will be used over there. All right, so next step is, so we have also created the pipeline. Now this pipeline can easily scale to n number of records, n sized file, infinite sized files, and whatever you want to do. Next thing is, since I want to build a model, is I tell my model that what are the inputs that it'll actually have to take. So it'll take all these inputs: trip start, month, hour, date, attitude, longitude, and even the distance. Over here, I'm specifying that my model will also take distance as an input. So what this actually means is that, and I'll actually talk about it in my future, in my next step. So I'm saying that month, hour, and day, these are all going to be string because I've marked them as categorical in pandas. I want to take it this way, but everything else is float. Okay, I'll run this thing. This is an important step. I mean, this is not it's not an optional step. This is how we tell Keras or TensorFlow that what are my features that are going to be used for training. Next step, and this is quite interesting again, is what we are going to do for the model training pipeline. So we have seen the data pipeline, but this is where we're going to see the model training pipeline. So we saw feature engineering which happened outside the model in the pipeline itself. So I created a parameter, a feature called as distance outside my model right now. But there are also some things that you can't do outside the model. They are preferably done inside the model. For example, I had those categorical attributes. Okay. Now the biggest problem with machine learning is it cannot understand directly your non-numerical signals like text. It cannot understand. It has to be transformed. Categorical attributes it cannot just understand. String signals it cannot understand. So we apply a lot of these techniques like one-hot encoding, hashing, and all those feature engineering aspects to convert a textual interpretation signals to numerical signals. Now we had so you saw that I had those month, day, and day of the week, month, and the hour of the day. All these three I've taken as categorical attributes. And how can I put them in the model? Is I'm going to apply one hot encoding, and you would quite pretty well know it. Okay. And also, if you remember from those gray heat maps that I created, I actually crossed two attributes. I was seeing fair as function of two things like trip start day and hour both together. How can I put that information in my model? How can my model see fare as a function of those two things? So I'm going to combine those two categories together. This is called as CrossJoin of categorical attributes. I'm going to create a new feature attribute, which is a crossover of trip start day and the hour, and put that as a feature, as a new categorical feature. And then I'm going to convert it as a one hot encoding attribute, or either as an embedding attribute. Okay, and all those attributes are going to be as the input of my neural network. So this is a very good representation of how the neural networks look like. So the lowermost layer is the input layer. You have wide models, deep models, and wide and deep models, which is a hybrid of this. In wide models, what happens is the input layer is absolutely very wide. It's huge. So assume it this way. Why can your model be huge? So let's say if you have a lot of inputs, let's say you have more than 1 million or 1 billion inputs, then your models can get wide. Deep models, when they have small number of inputs, but they are huge in size. They have a many number of hidden layers. Is when you have deep models. So your image models are usually deep models. Your structured data models are usually wide models. But since our data is like having both attributes, categorical and numerical, we'll prefer wide and deep models. So what we're going to do is all the numerical signals like distance, um, and even the other attributes I have, like I'll talk about them. So distance is one of the attributes. I'm going to put this as a deep signal. So, and the wide ones are all going to be categorical attributes, which I am going to convert and put them as one hot encoding. So let's say I have 12 months in an year. When I encode it as one hot, I'll get 12 new columns. Similarly, when I convert the 24 hours into one hot encoding, I'll get 24 new columns. So 12 plus 24 plus 7 is like already I have 41 new features that are going in as 0 and 1 signals. That is why I'm using this kind of a hybrid architecture, and it is state of the art. This design was given by Google as an estimator, and they're training a lot of these models, structured data models, using this feature. All right, the exciting part then next is finally how we're going to create a neural network. So here I've created a small structure. I'm specifying initial values of my learning rate. So I'm saying that my model will start training with learning rate 0.0001, and I'm going to use only one hidden layer. I want to keep my model simple and clean, but this can also increase. So you can switch onto these things. This is very specific to your problem statement. All right, so when I train the model, since this is a regression problem, when I want to predict the fare, so I'm saying that my metric that I want to monitor is RMSE, standing for root mean squared error. Okay, and I'm telling that that all the input features are the feature calls k. This feature calls k is coming from here actually. Create feature columns. It's coming from here. The same thing which we just saw above. And I'm telling that all these are the input features. Now, this is some of the interesting part, and this recently came in TensorFlow Keras, just released like a month back. So now in TensorFlow internally, you can actually do one hot encoding, you can do binning, and all those sorts of things. So what I'm doing here is, and I'll only cover one attribute from each category. So this is how you do a one hot encoding inside a TensorFlow model. So I can say that this is fixed. So I can say the function is string lookup. So here I'm saying that lookup each of these strings if my value in the data set is like 1, converted. So this function takes my string values over here and convert them into integer indices starting from 0. So let's say if I would have wrote this as cats and dogs and apples and butterflies, and it saw cat over here in the data, it would have encoded this into 0 as numerical. If it saw dog, then it would encode it as 2, 0, 1, 2, 3, and so forth. So it is converting my string signal to a numerical signal, and then I want to do a one hot encoding on top of that output. So I'm saying that after that, take my take my numerical signals from the above thing and convert it into a one hot encoding. So these are the two lines that you see, and I've replicated the same thing all the way for different categorical attributes. Second thing is binning. So I showed you that binning of latitude and longitude with those red lines. So I've done the same thing over here. So what I've done is I've taken that information, bins lat and bins lon. So this is the whole list of attributes that I had over there on top of it. And I'm telling that, hey, take this on top of it. I'm sorry, and there's some thing that I missed over here. Yep. Okay, so I'm saying that take all my latitude and longitude information and just bin it. So it is going to create the bins on top of it, basically. Okay, and this is how I'm converting my latitude and longitude numerical signals to bins. All right, and then categorical. So again, so these are next thing. So categorical cross, wherein I'm combining two or more categorical attributes to create a new categorical attribute. So I'm combining my day and hour because that's what we saw is actually a very important feature. So I'm combining my day and hour and creating it as a new attribute, and then I'm creating a hash over on top of it. Now hashing is important because it reduces. I don't have to specifically provide all the categories over here. My hashing algorithm will take care of all the possible values and will create a new hash for it in terms of that. And on top of it, this is one important thing. The next thing I want to talk about is the cross to embedding. Now, embedding is also an important feature. It's a sort of an advanced thing. I can't cover it completely end to end in this session, but I can talk about it a little bit in detail. So somewhat. So embedding is like whenever you have a lot of features, um, and there are relationships between different data points. For example, let's say I say I give a sentence that hello, how are you? Okay, and I say how are you doing? These two sentences have same meanings too, same context, but actually they have a different representation. Okay, there are different words, different number of words, different spellings, different sentence size, and all and everything, but the meaning is same. So embedding is a similar sort of a representation. It takes my let's say I want to create an embedding on top of this feature. So it will take this feature and anything which it sees that is similar. So for example, let's say uh, my trips are usually expensive at the end of the day and at the beginning of the day. So what it'll do is it'll learn certain things inside. The embedding layer will learn features inside so that it can encode these two areas specifically as a same entity and other things as different entity. So this is a very important aspect actually in huge models, in huge ML enterprise models, when you want your model to quickly learn relationships internally. And the good part is, once your model is completely trained, you can visualize them as well. So you can infer further complex statistics which you can't see just through your visual eyes. You can actually see them in tensor board, how your embeddings are coming up, and then you can derive more important aspects out of your model. All right. So next thing is, in the end, I'm saying that my deep attributes are all going to be my categorical ones. So the numerical ones. If you see pickup latitude and longitude, I've also taken it as a numerical signal as well, along with the categorical one. Distance is also going over here. I'm saying that all this should be taken up as an input, and then a new layer be created on top of it called as a dense layer with 32 neurons. Don't worry about this whole thing. I'll actually show you pictorially how this whole neural network and this whole junk looks like. It looks very difficult to understand, but I'll show you pictorially how this all looks. And then I'm taking all my categorical attributes from top of them and concatenating them as a new feature and putting them as a wide layer. On this input, I'm creating another dense layer of 32 neurons. So simple thing. The way that I did over here on the full concatenation of numerical attributes, I did the same thing for my categorical attributes. Now I have this X input numeric and X cate. Finally, I'm going to combine them as well together. So what we showed in this diagram, so we had sparse features. Those are the categorical ones, the numerical ones. I combined them and then I concatenate them over here. The same thing I am doing over here as well. I concatenate them. I add one more hidden layer on top of it. Then I apply batch normalization. Now batch normalization in neural net actually means that I am normalizing all my neural network outputs. So I am telling my neural network that stick to a mean of 0 and a variance of 1. That means in once I apply batch normalization, this is actually a trick to train your neural networks faster. And when you use batch normalization, you don't have to explicitly scale down your features, or you have to normalize your features. You need not do it. You can skip it. I mean, this is something which a lot of machine learning engineers, they don't know, but using batch normalization actually helps you do that and get through it. Then simple thing I'm telling, on top of it, add a single layer, single neuron, because I want to predict just one value. At the end of it, I want to predict the fare, and the activation is ReLU. ReLU is a value from all the way from minus infinity to infinity, sorry, 0 to infinity. Um, and just that's it. I'm specifying other options that I want to use an optimizer. So you have different optimizers are available on top of it. You can use Adam, you can use gradient descent, add a grad. There are a lot of good things available. Then you can change your these parameters also available. And I want to compile this model on my MSC model. Metrics is on the top, which I declared over here. So these are all the metrics. If you also want to monitor more metrics during training, you can go ahead and do that. I'll compile this. Okay, next I'm going to, so I've created my model, function to create my model. Now what I'm going to do next is, I want to specify a learning rate reducer. In Keras, you have a lot of callbacks. Callbacks provide you an option to further control certain variables during your training time or monitor certain values. So I'm not sticking to a certain fixed learning rate, but I'm telling my model that in case my model sticks, my model is plateaued on loss. If my loss does not reduce anymore, then it start reducing my learning rate by a factor of 0.2 with every epoch. This actually reduces my learning rate and also tries to further drill down the juice of the model right till the end of it. And then I'm also tracking everything in my TensorBoard logs. And then at the end, I'm in this function, I'll say start my training process. So these are all the callbacks that I'm going to reduce. And I'm also added one more callback called as early stopping. Early stopping is a reducer, is a preventer for overfitting. So in case if my model starts overfitting, then I want to prevent the overfitting. So it'll check that in case if my so how do you identify overfitting is, let's say your loss reduces on train set, but it starts increasing on your holdout or validation set. That is when you actually overfit a model. So here I'm saying that if my validation loss starts increasing and it increases continuously for 20 epochs, then restore the best model from the last complete run. These are some things which you can control, are very good in very much better in Keras models. All right, so that's there. And next is, if you remember, so I have created a make input function. I've executed them, and I've passed that as my inputs to the model over here. Validation set as validation set over here, and train data set over here. And this is where I'm linking my pipelines, my TF data pipeline to my model. So it's not reading from my file or pandas directly or my in-memory data set. It is actually reading data from my TF data pipeline, which will read in batches during my training process. All right. So once I've run it, I can actually see all the layers that are here in the model. But skipping this, I want to show you the pictorial representation of the whole graph. All right. So this is a very good representation of the machine learning model from the left-hand side to the right. It starts from left to right. You can see all the input features: train, trip start day, trip start month, pickup latitude and longitude, and all these transformations that are going inside the model. So you can clearly see that I took my trip start day, I applied a string lookup function, I did category encoding, then I did a category crossing between trip start day and hour, then I applied a hash function on top of it. And it's a beautiful representation of anything that you want to do. And then you see that all my categorical attributes are going as one layer, which have been concatenated. And this is actually a very wide layer. It has 264 columns. Okay, none means no number of rows specified, but 264 means number of, I mean, that's the width of it, the columns. And dense says it only has 5 inputs. Okay, but the output is like 32 only, 32 neurons, 32 columns. So this is actually dense, deep, but this one is wide. And then I've taken these two, I've applied batch normalization on the dense one. I cannot apply anything on top of it because because these are only 0, 1 columns. So I don't want to apply anything on it. It's already good. Then I've concatenated them together. I've created a new layer on top of it, which has 64 inputs and 32 outputs, applied batch normalization, and my final layer has only 1 output. Okay. This model will now learn everything. I'm going to train this for 50 epochs, and I'll show you that during this training process, it will take around like 5 minutes or so, around like 4 to 5 minutes, and we'll get a decent model which has validation RMSE of around uh, 3 to 4 units. So let's just hold on to it. So I'll take a pause before we go forward. We can hold on to any questions because this will take some time.
Yeah, so Asan, I have a couple of questions, and this has been an amazing demo till this time, right? Because it's a very complex subject. Typically, when we take a simple model and do a live session, but this is like
Yeah.
look going through the entire aspect of pipeline, how real world ML looks like.
Mhm.
You typically have your input data. You need to scale your input data. Pandas has a restriction where you cannot load data more than what it can fit in the memory. So you go to more kind of a distributed nature. And in that line, I have a couple of questions. So let me go with the first question. It says like for ETL, we can't use GPUs. Is that what you're referring to? I can add to
Yeah,
it if you want to get started with it.
yeah, absolutely. That's right. We can't use GPUs because this is a on-device problem. So GPUs don't usually help much as well on the in the data I/O. So I/O actually means when you're reading from disk directly. So it's only your CPUs which have to take effect on it. But adding, I mean, you can add to it, Shivatsan.
Yeah. So like, yes, when you're creating a TensorFlow pipeline, the ETL pipeline is going to be dependent on CPU. There are like APIs that are available where you can accelerate your ETL on GPUs, right? The Rapids API, but is that is outside of the scope of your TensorFlow pipeline. The other aspect, one good thing about TensorFlow is you can run it along with Spark. So you can use Spark TensorFlow. What you can do is you can use the distributed nature of Spark by default, and then use TensorFlow for the modeling part. So that goes well hand in hand. So that way you can also use distributed ETL processing over there. So that is one option that is available. Right.
Right.
So yeah,
And I
go
can
ahead.
also add, so you have something called as a TF profiler. A TF profiler actually helps you tune your IO pipelines, and I've used it personally. So if you use it well, and I've seen really fabulous results with using TensorFlow for IO. It curves out a lot of things that you can actually get it to that, because I think someone mentioned in the comment that there is a bottleneck. There is definitely a bottleneck, but if we apply the tuning steps on the TensorFlow pipeline very well, then it actually covers to major of those things.
Uh, Thank you, Asan. The next question is basically from Ali Wahid. He's asking like any specific reason for using tf.io gfile gblob instead of built-in gblob.
Yeah, so this was something, Ali, that when I was building the model, I did not look at that thing. But I think if you have different other options available, definitely go ahead and use them. But I think at that time, I did not have it. There was some deprecations that were happening.
Okay.
No specific reason for that. Yeah.
Yeah. The next question is again from Narayanan, who asked the first question on ETL on GPU. And this is also like, also while doing concat at using pandas, generally it is compute sensitive. Is there any alternative in TensorFlow for this?
Yeah. So you have a lot of TensorFlow functions. I think you also have concatenate in TensorFlow. And I personally use TensorFlow concat, and in at the end, in case if nothing works out, then you also have a tf.pyfunc option. You can write your own functions and pipeline them in a data set pipeline.
Okay, Hasan. And how are we doing with the training? Is the training done? We can continue and take the remaining question in the last, or do we have? Is the
Yeah,
training?
training is done. Training is done. I mean, we can take them in the end. So we see that a pretty decent model is trained and available over here. So we started all the way from. So there are these two loss functions. So loss RMSE. This RMSE is on the training set. And then this is the validation RMSE. It started all the way from 46 and 101. It went down. And something that I wanted to highlight is, see over here, you can see that my training or my validation loss actually stagnated. So my model reduced the learning rate to 0.0002. And then over here, it again reduced it further. And then again, it reduced it further. And my model is pretty decent. I'm getting a validation RMSE of $4.9. So if my trip was like $15 actually at the end, then my model can pretty much say, okay, it's like somewhere between 10 to 20. is my confidence interval between for this thing. So it's a very decent model. Definitely there's a lot of room for improvement, but that's not the subject for this session, because there were a lot of transformations which were applied, and there were a lot of complex ones that I did over here. But in a matter of time, I had to like put them and ease the session. Now, since the model training is done, we want to apply the model, and we want to see it. I think I also saw a question from someone on the chat which talked about training in serving skew. That is actually also what we're going to cover up. But quickly, so if I take the direct model, the output of the model, which is this m underscore thing which I created on top over here. Okay, if I want to directly use this for prediction, I can do that, but in that case I will also have to provide the calculated features from outside. Okay, so over here I'm giving you an example where I'm going to run this m underscore. I'm saying that I'm providing distance over here as well, but initially, but in real time, as an enterprise model, you don't want to provide your calculated features from outside, because that is a feature engineering step which is already applied inside of your model. Okay, so what I'm going to do is I'm going to save my model now, and in my model's own pipeline, I've created a new function, I'm going to create a new code over here, which is going to calculate the distance in the fly during my serving in my model itself, and provide it as an input to the model. So this is again an advanced option for TensorFlow serving. It's not necessary that you do this kind of a change on its serving pipeline, but this is again an option available. So I've added a new feature, and I'm saying that save my model. It saves my model over here. Quickly, it'll take like a 2 seconds for that, and then I can directly use this model. So again, I'm going to untar my model. So I'm going to tar my model through this. I can see what all things are available. I can run save model CLI. It tells me that these are all the attributes available. Currently, there's some problem going on with TF 2.4 TMS. That's why we weren't able to check this thing. But right now, I want to show you how you can load a model directly from disk. So what I've done is I had a model which was saved in the top, and now I'm going to run it. Okay, and here if you see, I've only provided the inputs that are available to me during prediction. I have not provided distance over here. I'll run it, and I'll see what is my output. Um, all right, so if you see here, it provided me 12.431375, and the output which was again available here was like 12.431375. So it computed the same distance inside the model itself, inside the pipeline, and it gave me the right result over here. So if you see, I did not provided any input over here. Everything is working fine. And with this, let me tell you for my closure statement, you can use the same code. You can train a model with any amount of data. You can host your model in the end. Once this model is exported, you can upload it on GCP, Azure, AWS as the final model, and directly ping it or send HTTP JSON request to get the predictions. So here is when I end my session. Let's open this up for questions.
Yeah, thank you, Hassan. Again, it was like an amazing end-to-end session, right? Covering all the complexity of pipelines and everything. When we talk about pipelines, when you think of scikit-learn pipelines, they are pretty easy because the API does it pretty simple, right? Like TensorFlow, in case of TensorFlow, the pipelines were an afterthought, and they are still building it. It's a long way to go. Maybe in TensorFlow 3.0, we can see a better pipelining concept. But the way you are covered it and everything on how to create a pipeline and deploy it, that was pretty good. Thank you, Hassan, for taking your time
Sure.
in the session. Right, I will get started with the questions. This is from Chandan.
Mhm.
So I think you kind of answered it, but what if the distribution of data differently skewed than the training set? Should we handle outliers here, or it's important for our model to know anything about unseen data? Maybe you can get started and I can add on to it.
Absolutely. So that's a good question, Chandan, and it's more around how you build your model, how you do the analysis. So any skew, so there are two things which there are two. Let me take it this way. There are two times when you have to handle this information. So one is before your training process, when you have to be sure that your training data is in line with production with your actual data, which is going to be. So you have to be sure that whatever you're training your model on right now, it's the same which is expected during the prediction time. Now, let's say you deploy the model, and after deploying, there are possibilities that after deploying your prediction data, it can change its distribution. Let's say your upstream system changed, or your business changed, or something changed, then your data can drift to a different distribution. There are systems that are applied in MLOps to make sure that your data is following the same distribution. And in case if the distribution breaks, then there are alerts, and then there are procedures, there are automated procedures tied up with it. It's more of a bigger process of ML ops, but that has to be monitored. So that's my short answer to it.
Okay, so next question is from Neeraj, sorry, from Hali Wahid again. Uh,
Mhm.
Ari's question is like, what's the primary purpose of TF data? Is to parallelize IO with model training. I have yet to find a way to know which of the both is creating bottleneck. Any suggestion on how to measure it?
Okay. So first question, TF data is usually used, you're right, it's used for ingesting data. So you can also ingest data through pandas, but let's say if your data grows beyond a memory and you cannot do it through pandas, then TF data is on rescue. Also, pandas provide, so with pandas, everything remains in a memory. You cannot get the most out of the juice of the model. The second aspect why you want to use TF data is you want to reduce queuing pipelines. Okay, training serving skew. So let's say I created my function, feature engineering function on top of it. Okay, now when I'm creating a model that is directly picking up from a file versus picking up from my change data from the memory in pandas, there's a lot of human error scope which is there. So let's say I did some transformation in my pandas which I probably missed to put in my pipeline uh, when I'm serving my model, then there is a possibility of training serving skew. That's why, I mean, it's a workaround that you use pandas for testing your models. But at the end of the day, to avoid training serving skew and to get the most out of your model in the end and your pipelines, you have to use TF data. So that's again, yeah.
Yeah, and Ali, to add on, right, and that's what we have seen in real world as well. Basically, pandas is good way to learn TensorFlow, but when we hand off the panda data frame to TensorFlow, basically we are using the scalability of the models. Now there are multiple way to distribute it, whether via Dask or even using the distribution strategy of TensorFlow. And TF data allows us to create a seamless end-to-end pipeline that we can take and easily productionize it, and leaving that pandas dependency. That is the main reason, like where TF data really helps.
Yeah.
uh, Next is from Ravi. Are we covering the part on how to use real world, like in mobile apps, or any light on that? So, Ravi, like here we are talked about deployment. Now, when we talk about mobile apps or even like edge deployment, right? There are multiple concepts that come into play, because sometimes the model will be very huge for even to load into mobile device, and the inference time may also be higher because most of the mobile device might not have hardware like GPUs and TPUs, right? So you have HTPU and HGPU, but that's different, right? So that's why like there are techniques like quantization and other aspect that comes into play. And maybe if you go to my model deployment playlist in my channel, you can see a lot on model quantization, on how to take a model and quantize it to make it lighter weight for faster inference, and that can be even used to deploy on TFJS or other aspect of it. But in this, we are not going to cover that part. What is the other question? Let me quickly check. Uh, Hasan, you got a compliment.
Yep.
It's a wonderful session, Hasan, from Harun. That's what Harun is telling. He's also asking like which third-party tool, if any, are using TensorFlow as their backend to create pipelines. Maybe a drag and drop tool having TensorFlow as backend.
Yeah. So Arun, I see. Thanks for your compliment. And answering your question, I see a couple of tools like TensorFlow Playground, but and then I saw a tool called as Percepti Labs and something from BMW Innovations as well. But so far, I've not seen anything which is really like solid in these lines. So let's see. Maybe we can hope that there's something which Google comes up in future. But I think that's something which I've not seen so far. Maybe I'll have to check on that. Never found a need for that, basically.
Yeah, that's right. I have not seen like any drag and drop tool for TensorFlow. Maybe it did not come to my notice. The
Mm.
Yeah. So this question is like, what are the approaches to imbalance binary class?
Oh, okay. So this is more around the I think how we are solving the imbalance problem. So it's a good question, and what I can say is there are two things. Either you can apply an sampling procedure where you can apply an upsampling, downsampling, downweighting. The second thing is in TensorFlow, there is something called as a class weights feature, a class weights parameter. So you can apply class weight. So let's say one class, one. So there are two classes binary in a binary classification problem, 0 and 1, and your class one has only 100 records, but the other one has like 10,000 records. So in that case, you can give a higher weightage to your lower class and the which is class one, and you can give a higher lower weightage to your abundant class. And there's a parameter in TensorFlow fit method wherein you can pass these weights, and then TensorFlow in itself internally takes care of training the model accordingly. This is also a good feature which I saw in TensorFlow. Thanks for bringing this up. Actually,
Uh, I think this is more like generic question on something I have been delayed from Neeraj Chopra. As I'm working on machine learning model deployment using Flask multi-class text classifier, eagerly waiting for its last video where it accepts 10,000 requests per second. And Neeraj, I am first sorry that I could not complete the second part. I am planning to have a live session this month, multiple live sessions, one using serverless and another using Kubernetes. Uh, I will soon post information on that either this month or next month positively. But I have something with the binary text classifier which is pretty similar, which is there in my model deployment playlist, which you can go and check it out, Neeraj. So that is something. But again, sorry for the delay. I think like that's the question we have
okay.
as of now. And again, like okay, I got one more question. Let me put that. It's from Neil. What resources should we look at to learn more about TF pipelines? Great session, Asan. First of all, there's a
Oh,
message as well
thank
for you.
Yeah, thanks, Neil. So basically, what I've gone through is there are some machine learning. So there are two things. One is a session on one is a video on Coursera by LAC, which is actually very good, which provides you more information on how you can use TF dataset pipelines. Then there are also a few machine learning crash course videos that are available. There are some available on GitHub, Google Cloud Platforms GitHub name, where you can find a lot of open notebooks which Google has uploaded them, and you can also use that information to build and train models on GCP as well. So I can share the link at the end of the video. I can put that as a comment, and then you can use it.
Yeah. I think like that's the question. There's one more like note from Harun. Like the session was really informative, Hassan. Again, like thank you for that. I think like that's about it for today's session. And once again, Hassan, thank you for your time and thank you for all the viewers over here who have been like watching this video with us and really being very interactive by asking the questions, which really motivates us to even kind of deliver more and be more productive during the session. Thank you very much. And I will end the broadcast now. We will meet in one other live broadcast here later this month. I have some interesting session coming up. So stay tuned to AI engineering. Thank you very much.
Thank you. Thanks, Yosin. Thanks all. Have a good day.